Okay, here we are. We're taking a look at your final unit. This is going to be done online, unfortunately, but we'll get through that. So, for your last unit, Unit 10, we got mechanical waves and sound. And honestly, this isn't going to be too bad. Here we see the big idea, number 6. It's the only big idea for this unit. You can read through that. And we have our learning goals, which you can read through that. Not sure how I'm going to assess these. If I'm going to, we'll figure something out. So, waves. All waves are named after water waves. So, a wave, basically the way we're going to think about it is a disturbance in a medium. If I take my hand and slap it in some water, water is going to, or the ripples from that is going to travel out from that initial disturbance. As I am making sounds, I'm creating a disturbance in air that's traveling out. So what a sound, or what a wave is a disturbance in some kind of medium. Now, what happens is that disturbance is going to carry energy and momentum. So as these sound waves travel from your speakers to you, what happens is those sound waves are slamming up against your eardrums. And whenever we have collisions, we have momentum being transferred. And also there's energy as well. Another example is if we throw a pebble into a pond. Once it strikes the surface of that water, there's a disturbance, and the energy from that disturbance and the momentum from that disturbance is carried outwards away from that initial strike. So, waves, a little bit of knowledge here, waves can propagate via different oscillation modes, transverse and longitudinal. So first off, a transverse wave, and you can pause this video if you need to write this down. It's simply a wave whose particle motion is perpendicular to wave motion. So a great example of that is if you were to take a string and shake it up and down. The disturbance will travel outward away from that. And you can see this example here. So the wave motion is up and down, and that causes this disturbance to travel away from it. So examples, water waves are always a great example of transverse waves, waves on a string, and certain types of earthquake waves. We're not going to get into this, but know that earthquakes are waves, and some of them are transverse. The second type is a longitudinal. Sometimes this is also called a compression wave. And this is a wave whose particle motion is parallel to the wave's motion. So think of a slinky, where you take it and you push it back and forth. So as you jiggle this one end back and forth, the wave propagates and moves away from that. Now there are a couple of important terms with this. So I'm going to get a highlighter here. The compression and the rarefaction. The compression is this area where we have more density. And the rarefaction is this area where we have less density. There's still a wavelength, which we'll talk about later, but I want to be very careful and point out compression and rarefaction. Those are two very important terms when it comes to these longitudinal waves. So again, that's a wave whose particle motion is parallel to the wave's motion. And again, you can always pause this video when you need to write down these definitions. So some examples. Sound. Sound is a very good example of this longitudinal, or I'm sorry, this compression wave. And also certain types of earthquake waves as well. But sound is definitely longitudinal. So waves themselves, you know, for the waves we're talking about here, these are mechanical waves, and they need a medium. They need something to travel through. Electromagnetic waves do not require a medium. So this graphic here, I think, does a nice way of showing this. So waves are broken up into mechanical waves and electromagnetic waves. Mechanical waves are either longitudinal or transverse. A couple examples here. They require that medium. Electromagnetic waves do not require a medium. So that's like light, microwaves, infrared, X-ray, all the different bands of EM radiation. Class example here, a little bit of fun, I guess. In space, no one can hear you scream. I don't recommend you going to space and taking off a helmet, but if you find yourself in that situation, no one will hear you. There's nothing for the sound to travel through. Sound, being a longitudinal mechanical wave, needs that medium. Now, some parts. This is some things that you probably learned in middle school. But we have our crests, which are at the tops here. Troughs, which are at the bottoms. Now the amplitude, you got to be careful. The amplitude is from the this x-axis up to the crest. It'd be like a negative amplitude if I go down to the trough. And then the wavelength is from one point of a wave to the same corresponding point. So you can measure from crest to crest, trough to trough, or just make sure you complete the S here. That's one wavelength. Wavelength, we classically use the Greek letter lambda. I don't know if this will let me draw it. It's not going to let me draw it here. It's the Greek letter lambda. You'll see it written elsewhere here. The time it takes for one wavelength to pass a point is called the period. And then if we count how many wavelengths pass a point per second, that's called the frequency. We'll get to those concepts here in a second. So again, amplitude, it's the maximum displacement from equilibrium. And classically, energy carried by a wave depends on its amplitude. And it looks something like this, where the energy a wave is carried is proportional to the amplitude squared. So if I double the amplitude, I actually carry 4 times the energy in that wave. Again, for a periodic wave, the period is the repeat time of the wave. The frequency is the number of repetitions per second. So for a periodic wave, the wavelength is the repeat distance of that wave. And we get a little bit of math here. This is very important. For this wave, its speed is equal to its wavelength times its frequency. So wavelength times its frequency. So again, here we use the Greek letter lambda for wavelength and F for frequency. And we'll take a look at that in a little more detail here in a moment. So let's take a look at an example here. Here I see a graph, and I see some y versus time. So y, think about this like a little kid with a rope, and they're wiggling that rope up and down. They're just going to town, throwing that rope up and down, and the waves are being transferred, being propagated outward. So first off, I notice I'm looking at a transverse wave. I see my crest, I see my trough, and all that. So first off, what is the period of this? So the period, if I were to complete this point, I can see going from this point to this point. That gives me like my wavelength. And I want to figure out the period of this wave. And actually, this kind of cheats for us here. We see it's going to be 4 seconds. If I take a look at this point right here to this point right here, if I do a subtraction, 7 minus 3, it's 4 seconds. So the period of this wave is going to be 4 seconds. Now, what about the frequency? Well, frequency is how many wavelengths pass a point per second. So if it takes 4 seconds for a wavelength to pass a point, and if I'm counting how many wavelengths per second, I would see that I would only get 1/4 of a wave per second. So really what the frequency is, it's always 1 divided by the period. So if I do 1 divided by 4 seconds, I get 0.25 inverse seconds. And inverse seconds has a special name. We call that the hertz. So frequency is measured in hertz. Now the next question, wavelength. Well, I can't find that out. If I look at this graph only tells me amplitude data per time. It does not tell me anything about the wavelength. So unfortunately, I cannot find the wavelength, and I cannot find the velocity because velocity is wavelength times frequency. I can't find that. But the amplitude, I can. I see the amplitude is 0.2, so 0.2 meters. Again, I can just read that right off of the graph, going from here over. Now, what would be the average speed of a single point on that wave? Well, over the 4 seconds, if we think about a point on that string, it's going to travel up to the 0.2 mark, then it's going to travel down to the negative 0.2, so that's a distance of 0.4. Finally, it's going to go back to its original starting point, which takes another 0.2. So if I look at like the displacement here, the displacement would be 0. But if I look at the distance, I would see that a point travels a total of 0.8 meters. So as this point on the string goes from here to here, and then travels back down to here, and then finishes up where it started. It would go up 0.2, down 0.2, down to negative 0.2, back up to 0. So it's going to cover a distance of 0.8 meters, and it takes 4 seconds to do that. So for a single point on that string, if I did 0.8 meters divided by 4 seconds, well, it gives me 0.2 meters per second. So the average speed of a single point on that wave is 0.2 meters per second. Also notice that when this wave travels, the energy and momentum travel, but the points do not. The points only go up and down. They don't start at the hand and work their way to the end of the string. So waves carry energy and momentum. They do not carry matter. What would happen to the average speed if the frequency were quadrupled? Okay, well, frequency is 1 divided by the period. So if the frequency is multiplied by 4, the period would be decreased by 4. So now the period is going to be 1 second. Initially it was 4 seconds. Now it's going to be 1 second. If I'm increasing the frequency, I'm able to fit more wavelengths per second. So that means it's going to take less time for a single wavelength. So now if I do my x over t, again it's going to be 0.8 meters divided by 1.8 meters per second. So notice that by quadrupling the frequency, I am also quadrupling the speed. I'm going from 0.2 meters per second to 0.8 meters per second. What would happen to the energy? Nothing. Energy is based off of amplitude, and frequency is not affected, or does not affect the amplitude, so we don't have to worry about anything like that. All right, moving on. Sound. Sound is a mechanical wave, so it needs that medium to travel through. That medium, though, can be gas, liquid, or solid. It's kind of weird thinking about sound traveling through solids, but they do. All the sound is a compression wave through a medium. So over here we can see a table on the left of various materials, their temperatures, and their speeds. And this is kind of an old table. It's measured in feet per second, but it kind of gets to the point across. So traveling through air at 32 degrees Fahrenheit, it's 1,087. If I increase the temperature of the air, it goes faster, and that's because I'm putting the particles in a faster speed. If the particles are moving faster because their temperature is higher, it's easier for that sound wave to go through them. In aluminum, it's 16,000 Well, if you think about it, in aluminum, the particles are closer together than they are in air. So it's easier for the compression wave, or that longitudinal wave, to zip right through there. Carbon dioxide, it's actually lower. Fresh water, we can see 4,000. Again, if I increase the temperature, the speed of the sound goes faster. Hydrogen, 4,000. Well, hydrogen is a less massive particle than air. Air is what, nitrogen? So because air is more massive than hydrogen, sound goes slower. It's harder to move those particles around. And then lead all the way up to steel. We can see that steel is real fast. So the speed of sound, again over here in meters per second on the table on the right, we can see if I increase the temperature, it gets faster. If I use liquids versus solids, anything I can do to get the particles closer together, that speed of sound is going to go faster. So some formulas here. If you want to calculate the speed of sound in air, here's your model to use. Now again, this is in air only. So the speed of sound equals 331 plus 0.6 times T, where T is the temperature measured in Kelvin. So at 0 degrees Kelvin, actually I take that back. I made a mistake. This should not be Kelvin. This should be Celsius. And let me correct my spelling. There we go. The reason for that, at 0 degrees Celsius, if I put Celsius in here for T, the speed is going to be 331. So again, if I come up here, air at 0 degrees Celsius, 331 meters per second. I see that right up here. So this is a quick calculation just to calculate how fast sound would be. It's a pretty nice calculation, pretty easy to use. Now with sound, we talked about frequency. Frequency is how many wavelengths per second we can do. How many times does a sound wave vibrate per second? And we can think of that like a music note. So if I come over here, I got this sound generator. I don't know if this is going to be loud or quiet on your end, but here we see a sound. If I go to a higher frequency, we hear a higher pitch, and if I go to a lower frequency, I don't know if you can hear that or not. So what we have here is we got a couple ideas here. So frequency versus pitch. Pitch is subjective. It's like how high or low the note is. Frequency is how we measure that, and we measure that in hertz. And there are three different, I guess, buckets, if you will. We got infrasonic, which is 0 to 20 hertz. That's too low for us to hear. Some whales and elephants will talk to each other in these low hertz. We can't hear that. 20 to 20,000 hertz, that's our audible. That's our hearing range. These are all averages. There are some people who can hear a little below 20, some people who can hear a little above 20,000, but for the average person, 20 to 20,000. 20,000 on up, there's no theoretical upper limit. That's ultrasonic. Bats use ultrasonic. We use ultrasonic to look at babies. So these are really, really high-pitched sound waves. And even though we can't hear infrasonic and ultrasonic, we still call them sound waves. They are still a disturbance in a medium. So when the medium and the temperature of the medium is constant, all three types travel at the same speed. So they're all sound waves. And just some fun things here. Animals that use echolocation must use ultrasonic waves. Audible and infrasonic have too long of a wavelength, and it causes the sound waves to pass around smaller objects instead of reflecting off of it. So echolocation is only ultrasonic. Again, pitch is the perceived highness or lowness. Frequency is the actual measurement of that. Finally, last thing in this video I want to talk about is diffraction. That's the bending of waves around corners. When waves pass through an opening, they become spherical, if you will. So flat waves become round waves. And also waves bend around corners. That's why you can hear someone talking even though you can't see them if they're standing around the corner. All right, that's going to finish up our first video. Hopefully this goes well. Bye.